Hello everyone, this is Jimmy and welcome back to episode 8 of Omnifactory. Yesterday we set up a bunch of automation for stuff like circuits and processors, and today I would think let's start by setting up automation for some of the machines we use the most. So I think that would be the wire mill, the compressor, the lathe, and the macerator. These are four basic machines they take very basic inputs. It's one item in, produces some number of item out, and we don't have to worry too much about doing, like, if we were to do the alloy smelter, then we have two items that come in at the same time, right? So by doing these basic machines first, we can do some simpler automation. These are also machines that process a large number of items. So instead of just using one wire mill to handle our wire milling needs, why don't we set up, let's say 8 for now, and set it up such that we can scale it up to using 16 to handle our wire demands. So let me build those machines, and I'll show you how I like to set up my distributed processing systems. Give me that CEF. Any day now. Yoink. Give me some wire mills. And there they go. This is mesmerizing. Next up, macerators. Compressors. Here they are. And lastly, lathes. And there's our last set of machines. I'll set up one set of these on camera. The rest will be basically the exact same. So let's do the wire mills first. So obviously they need power. So we're going to have 8 wire mills. And then we need a interface to feed into a buffer chest. Now, this interface, we should rename it so that we know what it is for. Otherwise, on the interface terminal, it'll just show up as small storage crate. We need to hook up our ME system to here. Let's turn our night vision on. And we need a P2P tunnel. What's happening? Why is it blinking out? Whoops. I guess that's why you shouldn't have a drill in your hand. Let me figure out what I did wrong. I probably hooked up the P2P net to the main net somehow. Yep, that's exactly what I did. Right here, I accidentally connected the P2P network to the main network, which meant I had 2 controllers on one network, which the system doesn't like. And turns out I might still have that problem. Did I do it somewhere else too? Doesn't look like it. Let's see if things work. It might have just been rebooting. So anyways, let's encode a pattern for our P2P terminal. And then we can craft these now. So that'll put this interface onto the network, and then when we request crafting from the wire mills, it'll put the items into this storage crate, and then we just have to feed items from the storage crate into our various machines. And then when the crafting's done, we have to take the items out of the machines and put them back in the interface. So now we have to configure these. And let's grab our copy paste gadget. All right, this should set up our wire mill block to be able to request crafting from it. Let's encode a pattern and test it out. So copper wire is probably one of our most used wires. We set it into processing mode and tell it that 1 copper ingot makes 2 copper wires. Actually, we use so much copper wire, I want to encode this pattern slightly differently. I want to tell it that a whole stack of copper ingots makes 2 stacks of copper wire. And if we come over here and look down here, we have wire mill, so we can put that in there. And then when we request copper wires, let's ask for 1,000 because we'll use 1,000. When we request it, we should see that all the copper ingots get dumped in here. And then this extracts from the chest and sends them into the wire mills. Now these wire mills are a bit faster than our conduit is extracting. So let's go get some speed upgrades for that conduit. And you see here, after importing the pattern, I'm correcting the recipe to use the right type of block. Sometimes you have to do that. So let's put 3 extract speed upgrades in there and then 1 into each of these. And now let's try that again to see if the conduits can keep up. So we'll go request 2,000 copper cables, a bunch of copper ingots get dumped in here, and look at that, every single wire mill is running. And this will be a lot easier than handcrafting all these wires. Now each interface can only hold 8 patterns, and we're going to end up with a lot more than 8 wire mill patterns. So what we can do is we can fit 4 different interfaces on this crate, 1 on each side and then 1 underneath it. And if we have to, we can just put a second storage crate here. Cool, huh? So I'm gonna do basically set up one of these for each of these other machines, the macerator, the compressor, and the lathe, and I'll be back when that's done. And here we have it, automation for each of the 4 most commonly used machines. Next, let's tackle some of the other assembler recipes and maybe take a look at the alloy smelter. We have to do alloy smelters slightly differently from the rest of these machines like the lathe because they take multiple inputs, so we can't just dump all the inputs into a chest and then round robin extract them. Because if we do that and say we make steel, we could end up with like the iron being put in this alloy smelter and the coal being put in that one, and obviously that doesn't make any steel. So instead what we do, at least what I'm going to do for now, is just set up 4 alloy smelters and distribute the recipes between their interfaces. That way, when we craft something, only one alloy smelter will actually do the craft, but we won't have to worry about the ingredients being split up in some silly way. Later, when we unlock something, when we unlock packaged auto, we'll have the technology to keep like the iron and the coal together all the way up until the alloy smelter, and that way we can set up these distributed systems for alloy smelters as well. But for now, this will have to do. So here are the alloy smelters. Next up, assemblers. When automating assemblers, there's quite a few variables we have to deal with, such as what fluid is in the machine and what program circuit is in it. So to accommodate that, we have to set it up such that for each different configuration of fluid and circuit combo, we have a single machine servicing it being fed by interfaces. So you see here, I set one up to do rubber with program circuit 28, and this is what makes the 16x covered cables. Likewise, we have one that does rubber with 24, which are the 1x covered cables, and then we'll have a couple more, we need 2 for polyethylene, and inevitably we'll need more than that. So let's finish setting this up. The reason we need 2 polyethylene assemblers is because of an interesting recipe conflict. So if you look at the recipe for transistors, they take these fine annealed copper wires, and the recipe for diodes takes small piles of gallium dust. But there's another recipe, this one, to make the basic diode that uses fine annealed copper and small piles of gallium dust as well. So if you put these 2 recipes on the same assembler and you try to craft them at the same time, you risk all the components getting dumped into the machine and accidentally ending up with the wrong type of diode. The next machine I want to hook up auto crafting for is the furnace, but instead of just using these regular electric furnaces, which are not bad, but they're a little slow for my taste, and they use a lot of energy for the work they do. There's a GregTech multi-block called the multismelter, and when you set it up, it looks a lot like a blast furnace, except it doesn't have the fluid input or outputs. So you set it up much like you would a blast furnace. And for this one, I want to run it off 2 high voltage energy inputs so that it runs pretty quickly. And unlike a blast furnace, it only uses 1 row of coils. And there we have it. So this multismelter, you see, based on the heating coil level, it smelts a different number of items at a time. So right now we only have access to these basic copper nickel coils, which are level 1, but as we go up we can get level 2, level 4, etc., and it smelts 16 items per level of the coil. So let's grab a chest and I'll just demonstrate how this machine works. And we can, I guess we'll smelt up a small batch of charcoal just to demonstrate. So input and output, and we'll throw our wood in here. See how every time this goes up, it smelts 16 items, which is much faster than an electric furnace would be. And right now this is only using these basic coils. We can upgrade this to when we upgrade to the higher tier coils, it'll go up to, I think you can do up to 4 stacks at a time with the highest tier coil. So yeah, the highest tier coils are level 16, which means it can smelt 4 stacks of items at a time. And with a system like this, I think we can finally make charcoal fast enough to feed these dynamos with charcoal instead of wood. So I'll swap out the chests for our interfaces, and then we can put our patterns in there for very fast smelting. On this side, from the output bus, because it pushes items, you can just put an interface there, and any items that get pushed into it will automatically get sucked into the ME system. All right, so now we have automated smelting available. Next, I would like to automate processing of the various metals we make in the blast furnace. So that would be aluminum, energetic alloy, vibrant alloy, and stainless steel for now. But the problem with these metals is that they take a really long time to make. So I don't want to do them on demand. I want to just have them auto processing in the background. So if you look at my inventory, I have all the supplies for 4 electric blast furnaces. At least I hope I do. I'm going to go set these up real quick, and I'll show you how I want to connect the ME system to them such that they will automatically produce the various metals we need when our supply is low. And here we have it, 4, I believe these are HV, high voltage, blast furnaces. The first step is to set it up such that they will turn off once you have enough of these metals in stock. So what I want to do then is put these machine controllers on the blast furnaces. That way, when the blast furnace receives a redstone signal onto that block, they can be configured to turn off automatically. So we can configure these to say this first one should be for aluminum. So if the aluminum level is above or equal to, let's arbitrarily pick a number, 5,000, turn this machine off. Next one will be energetic alloy. If we have more than 5,000, turn it off. Vibrant alloy, more than 5,000, turn it off. Same thing for stainless, more than 5,000, turn it off. Now these numbers we can change. We probably don't actually need, 5,000 stainless or 5,000 vibrant or even 5,000 energetic, but that's, you choose how much you want to keep in stock. Then the next thing you want to do is supply these machines with the raw material they need to smelt. So that'll be, let me grab them real quick. It'll be aluminum dust. Energetic alloy will take 2 inputs. And yeah, we'll go from there. Setting up the export buses for 2 of these will be very easy, and the other 2 will be a little more complicated. So let's start with the easy ones. The first one will be aluminum. We just export aluminum dust. The last one will be stainless steel. We just export stainless steel dust and give it a crafting card because we can just craft stainless steel dust from these various other dusts. The other 2 are slightly trickier. Because these take multiple inputs, I can't just put an export bus here and say export energetic alloy and gold, because at some point it'll probably end up, filling the entire thing with gold or energetic blend. So to fix that, we will use something called an impulse hopper. And this block, what it does is, when you put the capacitors in, if you configure it to say like this, it'll only transmit items when both, or when this, I guess we can call it a filter, when this filter is met. Whoops. So what I want to increase the count. There we go. I want it so that if we have 16 of each item, it'll transmit. Otherwise, it'll hold them in the top row, and only the bottom row here is will be exported into the machine. That way we can say that that way we can know that the machine will never jam up because it ran out of, or it got filled entirely with one material or the other. And they're not running right now because they take a little bit of RF, but right now I want to hook up all the components and then hook up the power and wiring. Oh, and one more thing, these impulse hoppers still need to have export buses on them so that we can actually send them items from the ME network. So this one, we will do gold and energetic blend. And because energetic blend has to be crafted, we need a crafting card in here. This one, since we're doing energetic alloy and ender pearls, we can once again put the capacity card in, but we do not need the crafting card because energetic alloy, we're not producing it on demand, right? We're auto processing it. So that's all we need here. And here we have everything once we drop all the wires in place. I added a crafting terminal here so we can see how much stuff we actually have. Let's just test really quick to make sure that these leveling meters will actually turn the machines off when we have enough. So this blast furnace here is making aluminum, and let's see how much aluminum we have. It looks like we have 3,600 aluminum, and this is set to 5,000. So if we set it down to 3,000, the leveling meter will turn on, and as you see here, this blast furnace now says work paused because we've met the threshold. But if we set this to, let's say, 3,500, and then we take some of these out so that we have less than 3,500, you see the level emitter turns off and the machine turns back on. So what this will do is it'll craft aluminum until we meet our threshold, and then it'll turn off. And then if we ever use some, such that we drop below the threshold again, it'll start making it again. And we have the exact same process set up here for each of these other materials. So this setup can be extended for all the metals we make in the blast furnace. Doing it this way, again, is better than doing blast furnace stuff on demand because of how long this crafting takes and the fact that we cannot run it in parallel. Well, we can't run all of the recipes in parallel. Stuff like these that use multiple inputs, we can't run in parallel yet. So this is the best solution we have for now. Next up, let's see. We've automated a bunch of small bits and pieces around our base today, but we haven't really done much tech progression. So let's see if we can, for our last project today, make us some titanium. The process for making titanium is a bit more involved than the other metals we've made so far. Not only does that have to be made in a blast furnace, we also have the blast furnace makes its hot titanium ingot, which we then need a vacuum freezer to be able to cool it into a regular titanium ingot. So a hot titanium ingot is made from manganese dust and titanium tetrachloride in a blast furnace at 2100 Kelvin, which I believe is actually higher temperature than what our copper nickel coil blocks can get to. So we'll also have to upgrade our coils. It also requires a high voltage blast furnace. The magnesium dust we already have from other processes, but titanium tetrachloride is made in a chemical reactor from carbon dust and rutile dust, another high voltage process, and one rutile dust and some chlorine. And one rutile dust produces 1 bucket of this, which I think turns into 1 ingot. Now looking at this, a lot of stuff goes into making 1 ingot of titanium. Besides the rutile dust, which is titanium ore effectively, you use 4 buckets of chlorine, some carbon, and 2 magnesium. But the other byproduct is this magnesium chloride dust, which can then be reacted with sodium dust to reclaim 7 small piles of magnesium dust and 3,500 millibuckets of chlorine. So you get, what is this, 7 out of 8? Basically you get 88% of your magnesium and chlorine back by reprocessing this magnesium chloride. So that was a lot of steps. The first thing then we need to do is make ourselves a vacuum freezer so that we can turn these hot ingots into usable ingots. Looks like that takes a couple tier 4 circuits, but otherwise nothing too bad. So I'll make that real quick and then we'll be right back. Alright, here we have it. 1 vacuum freezer, and I hope all the components we need to make it. And if you haven't guessed yet, it is indeed another GregTech multi-block. Now this one has a slightly weird shape, so I'll build it on camera just so we know what it looks like. It's 3x3x3, but the functional bits are in the middle layer. So I like to just bury the bottom layer one deep. And then we need a energy input, the controller, fluid input and output. Let's go left to right. So input, whoops, that's output. Output, no, input, output, there we go. Likewise for items, input, and output. And then the other blocks are these frost-proof machine casings. Whoops, and the middle block of the middle layer is supposed to be hollow. And then the top layer is another 3x3 of frost-proofs. And if it works, there we go, it should form. So the vacuum freezer, its only job is to take hot ingots and turn them into cold ingots. If we look at the recipes it can do, or no, I lied, it has two jobs. It can turn water into ice and air into liquid air. This one will be very important later, but what we're using it for now is just turning regular ingots or hot ingots into regular ingots. So to do that, what I'm going to do is put a storage crate on the input side and put a export bus on the storage crate. And what we'll do is we'll just fill this with all the types of hot ingots we make so that when they get crafted, they'll automatically get sent to here, which will freeze them. And then we can, after they're frozen, import them back into the network. So the first type of hot ingot I think we have to make is canthal, which will be the coil material that we use for our tungsten, or yeah, for our titanium. So canthal isn't all that difficult. It's iron, aluminum, and chrome dust mixed together to make canthal dust. And then this will just go into a blast furnace, which will cook it, and then the hot stuff gets frozen. So I think because it's very similar to the stuff we're doing here, I'll just extend this one more and put another blast furnace right here that'll process our canthal. So here's our canthal blast furnace. It's very similar to our other ones. We have an export bus sending canthal in with a crafting card and a level emitter that we haven't configured yet because we don't have a canthal ingot to configure it with, that will disable the machine when we have enough. So it's been running for like a minute, and you see here we have 9 hot canthal ingots because that's what it produces. So what we'll want to do with those is add them to this filter here, so that we can automatically export them to here. But there's a small problem in that, take a look at this. When I pick these up, I start getting hurt because I guess they're burning hot ingots. And, well, the time it takes for me to grab the ingot from the terminal, move it here, I might die. So, you think maybe there's some type of gloves you can wear so they don't burn you. If there is, I don't know about it. So what I'm just going to do is make a ME terminal to put right next to the blast or to the freezer so that I can easily add stuff to the list. So let's put this here. And now what we can do is take the canthal ingots, come here and say export those to there and put them back so that I don't die. And we'll see the canthal ingots are being sent directly to the vacuum freezer, which freezes them and dumps them into this interface where we can now see we have access to regular canthal ingots. We don't need a terribly high amount of these, so let's set this maybe to like 200. I think 200 canthal ingots will serve any like one-time needs for it, and if we need more than that, well, it'll let's set it a little higher. 400. 500. So we'll keep 500 canthal ingots in stock this way. And now that we have access to canthal, once we've cooked up enough of it, we can make the canthal coils, which will let us start cooking titanium. Our inventory is now pretty cluttered, but I think this should be pretty close to everything it takes for us to make titanium. So again, if we look at titanium, the first step is to make this titanium tetrachloride, which is chlorine, rutile, and carbon dust in a chemical reactor. because it has multiple solid inputs, we have to use an input hopper to keep it from jamming up. So let's do that. The impulse hopper, we'll configure it to say give 1 rutile and 2 carbon at a time. And we'll have it push to the side. That will go into our first chemical reactor. This will also need some chlorine, so let me grab a sample of that. So when we give some power here, all right, so this will, that should be, oops, I broke it, hold on. 2 carbon and 1 rutile, which we also need to put into the export bus. And for now, we don't have much rutile ore, but we'll get more of that pretty soon, I expect. There we go. So that should be sending both carbon and rutile ore into here. This chemical reactor will turn it into carbon monoxide and titanium tetrachloride. Carbon monoxide has some fringe uses besides breathing. So I will store it. And I guess we haven't made the recipe for this yet. Let me add a recipe for quantum tanks and I'll be right back. And we're back with the quantum tank. So this produces carbon monoxide and titanium tetrachloride. We'll store the carbon monoxide in there and just void any excess. And we'll store titanium tetrachloride in there. So let's grab our fluid conduits and some filters. So put our conduits down, connect the filters. For the trash can, we want it low priority and carbon monoxide only. So I have had some people ask how you do this drag and drop thing. For me, it's just when I have the fluid filter open only for Ender IO filters. If you left click on a fluid, and you can let go of the mouse button after that, then you can left click in one of the filter slots like so, and then as far as I can tell, it only works on these fluid filters. It doesn't work on stuff like storage bus. If you do it on a storage bus, it just pulls up the recipes for how to make it, unfortunately. Anyways, continuing on, we'll continue to set our filters. Alright, so the reason I have a storage bus on our titanium tetrachloride buffer is that this stuff has some fringe uses as well. It can be used as part of in our polyethylene production. We can, by using a little bit of it, we can significantly increase our polyethylene yield. Right now, we get what, with tetrachloride, we get a 1 to 2 yield. Without it, we get a 1 to 1.5 using, if I can, well, it won't show here, but yeah, later when we have more rutile, I'll happily siphon off a little bit of this tetrachloride to increase our polyethylene yield. So now that we have titanium tetrachloride, we can use that in a blast furnace to make titanium. So let's set up a blast furnace right here, and that's what these Canthal coils are for now. The item input that goes into here will be magnesium, so we also need to make sure we're ready to pump items as well as fluids into there. Any day now drill. For some reason, the actual additions drill is very slow at breaking coil blocks. So we want to export magnesium dust from here. And there we want just to transfer the fluid. And then we should see this blast furnace turn on. It's cooking the hot titanium now, which looks like it takes 40 seconds per ingot. So it takes a fair amount of time, and since it's a high voltage recipe, this isn't overclocking any. When it's done, the results will go into here. So let's take the items out of here and put it back into our ME system. And then we should see that we have at least one ingot of hot titanium ready. There we have it. And we just have to set it up to freeze it. So we take it, let it burn for a few seconds, add it to the export bus, and then let the export bus send it to the freezer. When it's done, voila, a titanium ingot. So let's also set up the same control logic that we set up for the other metals, so we can turn the blast furnace off automatically. So a redstone emitter here, a machine controller there. I should have grabbed that titanium ingot we had. And we'll set you to maybe 1,000 for now. $20 channels on this already, wow. Alright, so when we get over 1,000 titanium, it'll shut this off. And just so we're sure, I'll set it to 1. And we see it turns off and the machine pauses. And when we set it higher, the emitter turns off and the machine starts running again. So now that we're producing the titanium, we also have this, what is it? This magnesium chloride dust. And we can reclaim most of the magnesium and chlorine that we put in by reacting it with sodium. So let's set up that chemical reactor next. And since this step is like a bunch of things we've already done, I'll just do it off camera and show you the final result. And here's our whole reprocessing system. We are sending the magnesium chloride and sodium dust into an impulse hopper that feeds it in the right ratios to this chemical reactor. This chemical reactor then will be will react the two and turn them into these small piles of magnesium dust, which we turn into big piles of magnesium dust, the regular magnesium dust. And then we will import bus that into the system, which apparently I forgot my import bus. So So we'll use an import bus to grab that back into the ME system. And then this will also produce this chlorine, which we will extract and send into here. And this chlorine, we have a storage bus on it that has very low priority. So again, it will be used before other sources of chlorine. And what will generally happen is this chlorine then will get sent over to here, where it'll be reused to make more titanium tetrachloride. And this process then will automatically produce titanium for us. So I think we can call this episode here. I have a feeling we're comfortably over the 30-minute mark already, but that's fine. We had a good episode, and I think the first half of it, we automated a bunch of small systems that'll be useful in just reducing our manual workload. And for the latter half, we managed to automate our titanium producing process. All right, well, I hope you liked the episode, and I hope to see you in the next one. Take care. Bye-bye.